John Bedford and Nicholas Payton. Today we're going to talk about the spray booth pressure system. So in this 10th week review, we're going to cover the spray booth system, the steady-state operating curve, the step response, the frequency response, the relay feedback, root locus, and then we'll do a conclusion. There's quite a bit of slides because there's a lot of things to cover there. So the first few we're going to go through kind of fast and not hit too many highlights on those. So this is our spray booth system. In our system, dampers 1 and 2 are closed the whole time. The power is adjusted here, and that gives us a pressure and cms of water, centimeters of water. So we have the input, which is the motor power, and the output, which is the centimeters of H2O. This is a first initial step response. We developed a steady-state operating curve based on similar examples of these. We ran about 5 per team member, and this circled area here is the steady-state area that we used for our data. Using that data, we built the steady-state operating curve, and for the most part, ours came out fairly linear, which is what it's supposed to look. There's a little bump here and there. And we'll actually use this later when we're talking about the relay feedback. This is the modeling of the step response. You can see we had a fairly good, if you look here, you can see our outputs, our inputs lined up fairly well, as you would expect. Our curve here for our output lined up pretty decently. There's maybe a little corner here, but it was a pretty good fit. You can, if you look up here, where our gain came out to 0.7, our dead time was 0.2 seconds, and our tau was 0.1 second. This was a frequency response. This was done by the other team members as I was on the alternative. I didn't do the frequency response. The frequency response had a different gain as the slide before, from which could be the difference in values, since this team member was on a different range of outputs. So the gain here was 1.3 centimeters of H2O per percent. The ultimate frequency was 3. The critical gain was 2.5. Tau was 0.2, and dead time was 0.1. This is a picture of the relay feedback, which was the alternative for that. It's quite busy. Here the T is measuring the time from here to here, and that's the delta C. The time is from here to here, the length of that time, and then the delta C is from this point to this point. Those were done for each of these waves, and that averaged out. Now, on the relay feedback, you had options to adjust the set point and the floor and the ceiling. In the experiments, I was asked to go through and figure out what happens when you change the set point. So what I did was I kept the floor and the ceiling at the same spot, which was the floor was at 20 and 20% input, and the ceiling was at 80% input. And I just moved the set point. So you can see if you look here, the set point would be about 17 here, and then the set point for this one was around 25, and this changes your critical gain, or and then the this line right here is your ultimate frequency. And you can see as you increase your set point, that the frequency increases and the ultimate frequency increases and the critical gain increases. From there, I set the set point back to 8 and the floor on 20, and just manipulated these ceilings. And you can see the results here are actually sloping down, whereas on moving the set point, we increased in frequency and we increased in the critical gain. But moving or increasing the ceiling actually decreases those values. And this graph kind of came out odd. I would probably like to go back and do more experiments to see if it was just, if this is a turning point or if that's just a mistake, outliers. So here we just moved the floor and we kept the ceiling at 80, the set point where it was supposed to be, and moved the floor down. I think it started around 30 or 25 and moved down to about 10. And in doing so, you can see as we increase our floor, it doesn't really have a specific pattern. It goes down and goes up and goes down. It may, if we were to do more experiments, it may oscillate. So going back through, it would be nice to do some more experiments to kind of find out what that actually would do in the long term. Now, in manipulating these things, you could have a system where the power of your motor was maybe a little on the high side and you needed to adjust your frequency. So you might can manipulate like the floor, the ceiling, or the set point in order to meet those. If your motor is a little too powerful or a little too weak, you might could adjust your outcome based on changing your parameters. So in order to set the relay feedback correctly, we would use the steady-state operating curve. You would find a point like here on 40% input. Here you would have about 9 for your set point. So you would set your set point at 9, and then you would set your your ceiling 10% above, and your floor 10% below. And that was done using this slide right, this control input. So the length of the experiment was 20 seconds. The baseline was the 40 that we picked from our steady-state operating curve. The set point was 8, could have been 9. The floor was 30, the ceiling was 50. This is the root locus. This was done by another team member. My root locus was a little different and had a little bit different inputs based on the experiments that I had done and the fact that I did the relay feedback based versus doing some of the frequency response and the bow diagrams. So we talked about the spray booth system, how our inputs and our outputs, that the dampers, both dampers were closed. We talked about the steady state operating curve and how we use that to set our relay feedback. We talked about step response and the results from the step response, the frequency response, and the locus. We also discussed how changing the set point, the floor and ceiling adjusted our outcome, our output.